Hey, hi, all. Welcome to our module 1 of LLM Security Professional, where we are going to focus on LLM fundamentals and architecture. So, let's start with this module. So, LLM fundamentals and architecture. To secure AI, you must first understand how it works. What are the key principles of AI? Without that, if you directly delve into it, it might be difficult to understand, right? So, we need to have our right basic baselining, right? Now, this module opens the hood, how LLMs are built, trained, and how they generate text. So basically, we're revolving around LLMs like large language models. How do they get built? How do they get trained, and how they generate the text, and where security control must be applied. What are the avenues of applying the security control? Right now, why this module matters is that like every AI vulnerability you will learn later will trace back to something what we are going to cover in this module. You can't define a system you don't understand. So this model is focusing on the the infrastructural attributes, what we are need to protect, how it is built, and then we will connect each technical concept with the real security risk. So what we'll learn is like how attention work. When I say attention, consider it as a keyword in the context of the architecture we are going to discuss. So how attention works. If we lack this, then later we'll understand how prompt injection will be in the context. How attention plays an important role when you understand the principle of prompt injection. Then how models are trained. Data poisoning. This will help us to secure on the lines of data poisoning and model theft. Inference setting, denial of service and cost attacks. RAG, which is retrieval, augmented generation, and fine tuning, which is retrieval and supply chain attack, focusing on the security aspect of these areas when we learn this. So, the learning objective is by the end of this module, you will be able to understand the transformer architecture and attention, explain the training pipeline, which is pre training to SFT to RLHF to constitutional AI, then describe inference parameters, which is like temperature, top P, max tokens, and their security impact. Differentiate major LLM providers and deployment models. Assess the security trade offs of RAG, fine tuning, and quantization. So let's start with the very first thing, what is an LLM? LLM is a large language model, is a giant next word predictor. Basically, it's a next word predictor. It works on a prediction mechanism. We'll understand this how it works. It learned pattern from huge amount of data or text, which is like books, websites, code. It doesn't look up answers. It doesn't look for answers the way Google and other search engine works. It doesn't look for things, but it predicts the most likely next token over and over. So it works on the prediction. For example, if I give or ask like the capital of France, so it will predict it. Okay, it will predict the next most possible token, which is actually going to suffice the answer, right? Which is Paris. So it will give us the Paris as a response. So that is how it works. So you can consider the analogy of it is like autocomplete on our mobile phones, right? It is being supercharged in billion times, and then we'll get to see the next predictable word to help us to autocomplete a particular word or a sentence, right? So let's go for a trial now. So this is a third party solution called as Polo Club, github.io.in. I'll just copy this out. So this is a transformer explainer, okay? I would suggest you get to it. Let me just put it. So if you see here, we have examples like data visualization empowers to user to create, okay? So this is an example like data visualization empowers user to create. So this is just written here. So transformer, what is a transformer? We need to understand that first. So transformer is the core architecture behind modern AI powering models like ChatGPT Gemini. Introduced in 2017, it revolutionized how AI processes information. The same architecture is used for training on massive dataset and for inferences to generate output. Here we use GPT-2. which is small, simpler than newer ones, but perfect for learning the fundamentals, right? So this is using GPT-2 and how does it think. We'll also understand how does KV works. But to start with, this is our thing. So example, artificial intelligence is transforming. So what it does is, it is, these are the embedding, like data visualization empowers user to. So if you see, these are broken into the tokens. This is our input given to the GPT-5, for GPT model 2, GPT base 2, GPT-2 is small model, right? And when this is given, it is broken into tokens like this. So data visualization empower user 2. Okay, then it is becomes query key and value, and then it is fed to MLP and the residual, and then it is going to give us the probability, which is going to be the next word in this. Okay, so it is currently examples. So artificial intelligence is transforming the way. So the next predicted word is way. Similarly, I can see as the spaceship was approaching. Now, transformers are on magic. They build text step by step by asking what is the most probable next word that will follow the input. So basically, that is what transformer is. It is going to predict most probable next word. Here we explore how a trained model generates a text. Write your own text or use an example to and click generate. Although I'm not getting the option to have a generate, if the model isn't ready yet, try another example. Okay. Now, transformer architecture, you need to understand. First, we have something called as embedding, which turns text into numbers. So text into numbers. So this is embedding, basically classifying it into smaller tokens. Now transformer blocks mix information with self attention and refine it with an MLP. And probability. So there are three sections: transformer block and probability. So embedding is something which is tokenization, and then we have transformer block, and then we see probabilities, which is determining the likelihood of each next token. Now let's click on the embedding. What does embedding do? It create basically do the tokenization part. If you click on tokenization, it splits input text into tokens, small unit like words or part of words. GPT-2 has 50,000 token vocabulary, each with unique ID. Now in the token embedding steps, every token is matched to 768 number vector for large lookup table. Now these vectors are learned during training to best represent each token meaning. Okay. Now, positional encoding word order matters in language. Positional encoding gives each token information about its place in the sequence. GPT-2 does this by adding learned positional embedding, right? So the key is, we have embedding where we do the tokenization, then we have transformer block, which is the main unit of processing in the model. It has two parts: multi-head and self-attest attention. Let's token share information, MLP, which refines each token in detail. Models stack many blocks so token representation becomes richer, and they pass through. GPT-2 has 12 of them. So self attention is lets the model to decide which part of the inputs are most relevant to each token. So this helps us to capture meaning and relationship even between far apart words. So in multi-head form, the model learns on several attention processes in parallel, and each focusing on different patterns. So self attention means it will try to understand which word has more attention, right? Basically the QKV which we are seeing here is query, key and value. So what is going to be queried, what is the key and what is the value, like that. We'll understand it in great detail in the upcoming slides, right? So for our given, as the spaceship was approaching the planet, right? Planet, surface station, these are the next possible words which we could see here. Yeah. And the probability of having a planet is more. So that's why it is given as an output here. So query q value, this is again query q value which is here, right? So to perform self attention, each token embedding is transformed into new embeddings, query q and value. This transformation is done by applying different weights and biases to each token embedding. Now these parameters are optimized through training. Once created queries compare with keys to measure relevance, and relevance is used to weight the values. Okay. Now multi-head, after creating Q, K and V embedding, the model splits them into several heads, 12 in GPT-2 small. Each head works with its own smaller QKV, focusing on different patterns like grammar meaning. Now, masked self attention. In each head, the model decides how each token focuses on others. Dot product, mask, and softmax. Then attention and concatenation, which is the key step. Then MLP is a multi-layer perceptron. The attention output goes through an MLP to refine token representation. A linear layer changes embedding values and size using learned weight and biases, and then a non-linear activation decides how much each value passes. Many activation type exists GPT-2 using GELU, which lets small values pass partially. Output logic, which is all the transformers block, the last token output embedding, enriched with context for from all the previous tokens. It's multiplied by learned weight and final layers. Now the producer's log gets 50,257 numbers fun for each GPT-2s. And probabilities are just raw case scores to make them easier to interpret. We convert them into probabilities between 0 and 1 where all add up to 1. Now this tells us the likelihood of each token being the next word. Okay, so these are the likelihoods. Now temperature is very important because if you set a low temperature, makes large logit events larger and smaller ones smaller, favoring the highest scoring tokens and leading to more predictable choice. If you want more predictable choice, lower the temperature value. If you want uh, more creative outputs, then increase the temperature value, right? More creative and more liberal, but you want exact answer, then you need to keep the temperature value low. Similarly, we have top K, which is sampling strategies. Like finally, we need a strategy to pick up the next token. Many exist, but here are common ones. Greedy search picks the top one. Top K keeps only the K most likely tokens, and top P keeps the smallest set whose total probability is set at least P time. The soft max turn into remaining log. It's okay. Then residual connection is transformers have auxiliary features that enhance the model's performance. For example, residual connection adds a layer or input to its output, keeping information from fading through many blocks. Okay. Dropouts are random turns of connection between numbers so that model doesn't overfit. Okay, that's fine. So again, we are so this you can go and check. You can even provide, although I'm not seeing that option here, but we do have an option to provide our own. Yeah, you can provide your own. See, so what is the capital of France? So it has taken up and then it is giving question mark. Okay, question mark could be the next word like that. Let's give it with question mark and let's see what is the next probability word it is going to see. It is going to give that we can give a new line possibly. But if I don't give a new line, let's see what it is going to generate. Okay, if I give the capital of France is, the or Paris. So Paris has a lower predictability, but if I want the exact value, or maybe let me just change the temperature value and let's see how does it give us a response. The capital of France is the city. Okay, like that it is given. But if I change the let K be maximum, what does it give? Suburb. Okay, like that. Top P. Hmm. So yeah, this is how you can play and check what could be. This is how the transformer works. So that's the key here that I want to explain is about transformers. Now that is the thing which I have to explain. Then next thing is you can go and try this thing. Now transformer, it was introduced in 2017. Attention is all you need. So attention is something which is the focus. Powers every frontier model, GPT-4, Claude, Gemini, Llama. Replace older RNN and LSTM models that read one word at a time, slow and forgetful. Basically, before transformer we have this RNN and LSTM which is slower. Now transformer superpowers look at all words at once, fast to train, better at control. So analogy is like an RNN reads a sentence through a keyhole, one word at a time. A transformer lays the whole page on a table and connects related word instantly. So self attention is the core idea. Now attention equals to each word decides each other word matters to it. For every word, the model builds three vectors. So basically, there are three vectors: query, key, and value. So query is something what I'm looking for, a search box. Key is what do I offer, a label, and value is the info I pass on the content. So the words matching Q, K pay more attention to each other. So what Q, K in lectures? Every word in a sentence asks a question. Every word wears a label, and every word carries some information. So attention is just word finding the other word that best answers the question. Now the dog didn't, example is to understand it better, is the dog didn't cross the street because it was tired. Now it refers to whom? It pays high attention to dog than to a street, right? So that is what the attention mechanism is. So you can try it in again in here, like we have a Google collab called as BertWiz. So I'll just take you to here, BertWiz. So there is this link which you can directly come and check. It is good to run. No, you don't need to run that. So you do not need to execute any cells. Scroll down and preload visualization. So basically come here and then see. So we have the input like the cat sat on the mat. So when I click on mat, the bold line, if you see, right, like the on cat effect. So there's a dark line as well as then these lines are hovering. If you see, shows the attention mechanism, right? So you can go and check this out. Basically this is already available. So these are the connections between these tokens, and for each word if you see, that it will show how it is connected to uh, the other word, right? What is the attention mechanism which this token is giving to other token, like that. So what I'll do next is we will study more on the transformer engine or self-attestation mechanism. Basically, for moving forward with causal and multi-head attention in the next lecture, because there are two hand functions which you can perform and understand how the probability things works in the modern LLMs, right? So stay tuned. Thank you.